Hey grade 9, welcome to Unit 2, Section 2, Multiplying and Dividing Powers. So in this lesson, we're going to use exponent rules to multiply and divide powers. So we're going to start with an investigation, and we're going to kind of look at some products or some powers that are being multiplied and expand them, and then see if we can write them as a single power based on what the expansion looks like. So let's start with this first one. So if we have 3 squared times 3 to the 1, well, this would be equal to, well, 3 squared, of course, is just 3 times 3, right? And then I'll leave this dot here just to show the position, right? Then we have 3 to the 1, which is really just a 3, right? So this is really just 3 times 3 times 3, which is 3 cubed, right? 1, 2, 3. We can write this as a single power because they're all multiplied, right? And they all have the same base, right? The next one, 3 squared times 3 squared would be 3 times 3 times 3 times 3, which is really just, again, here we just have, 4, we see the base 4 times, right? And it's the same thing. This is, again, another power we could write as a single power, but this time there are 4 of them, right? Well, let's do this last one that has this dot. So here again, 3 times 3 dot, and this time it's 3 to the power of 3. So this power over here is going to look like 3 times 3 times 3, right? And so now we have 5 of them. So this is 3 to the 5. Okay, so each time here, we've been able to write this expansion as a single power because really we just have the same number being multiplied, the same base showing up in a series of multiplications, right? Which is how a power works, a single power. What about if we were adding 3 squared plus 3 to the power of 3, or 3 cubed? Well, this one would look like this, right? If we expanded it, it would be 3 times 3 plus 3 times 3 times 3. Right? Now this, of course, is going to compute to, well, I'm not sure what it'll compute to, 9 plus, well, actually we can figure it out. It'd be 9 plus 3 times 3 times 3, which is 27. All right, and this would actually be 36. Right, now is this equal to 3 to the 5? Right? 3 to the 5, right? 3 times 3 times 3 times 3 times 3, that's actually, right, in the hundreds, right? It's 241, I think, to be exact. So clearly this is not the same as 3 to the 5. Okay, so this cannot be written, right, as a single power. What about this next one? Well, this time we have 2 times 2 times, and then the second power is 3 to the 3. So again, 3 times 3 times 3. Now, can we write this all as one power? Well, obviously we can't. We don't have the same base here, right? We start with 2's, but then we get 3's, right? And as soon as that happens, really, we're not seeing the same thing repeated 5 times. So this is also not equal to 3 to the 5 or anything like that. Let's move on to the next one here. Well, here we have x to the 4 times x squared, right? This time we get x times x times x times x. There's 4 x's, that's the first part, and then the second power, x squared, well, really we're just going to get 2 more. And really this just means multiplication, right? Whenever the letters, you see letters next to each other, it all means times. And so here we have literally got 6 x's all being multiplied. And so we can write this as x to the 6. And we should cross these off because we couldn't do anything, right? There's no single power. So this was only possible, right? First of all, to do this, to write a single power when we had the same base in the whole series of multiplications, right? And it was only possible when everything was multiplication, right? This did not work here when we had plus. So in general, if you have, and this is the key, if you have the same base, right, 2 powers with the same base, and you're multiplying them, okay, then you can just simplify this process. Well, look at the pattern here. When we did 3 to the 2 times 3 to the 1, we got 3 to the 3. Well, 3 is just 2 plus 1, right? 4 was 2 plus 2. 5 was 2 plus 3. And of course, 6 was 4 plus 2. In other words, you can add the exponents in this situation. So this is really just b to the m plus n. And the product rule, okay, which is a vocabulary term that you should know this definition. To simplify multiplied powers with the same basis, we add the exponents. And of course, this is the key. They have to be multiplied and they have to have the same basis. So what if we're dividing powers? Let's move down a little bit here. So let's use this table to investigate what happens when we divide powers. Well, let's expand this. 3 to the 3 divided by 3 to the 1. What does that mean? Well, we'll write this using a fraction line, first of all, right? So let's do this. We're going to have 3 to the 3, right? So that's going to be 3 times 3 times 3 all over 3 to the 1, which is really just a single 3. Now, how can we write this as a single power? Well, hopefully one thing you remember is that when you have a series of factors, a series of things being multiplied in a fraction, or a bunch of fractions being multiplied, you can cross off any common factors from the top and the bottom, from any place in the series of multiplied fractions. Well, this is true even if you have a bunch of things multiplied in the numerator, right? So we have 3 3's up here, and we have 1 down here. What this means is that we can divide both the top and the bottom by 3, and that's going to get rid of one of these, right? And one of those. And whenever you divide off the bottom of a fraction like this, there's still always a 1 left over, right? So don't forget what we're doing is dividing each of these by 3, and that leaves a 1 down there, which effectively gets rid of our denominator because dividing by none does nothing. So how can we write this then as a single power? Well, all we're left with is just 3 times 3 in the numerator, right? Which is 3 squared. Okay, let's do this one. Well, this time we have 3 times 3 times 3 over 3 times 3. That's 3 squared in the bottom, right? And this time, you notice how we actually now have 2 in the bottom, right? So for each of these, we can cross one off up here. And so this one will cross off with this, and we'll have 1s left over. And then here, these 2 will cross off as well. So on the bottom, we have 1 times 1. On the top, we have 1 times 3. Right? So this is really just 3 to the 1, because nothing is left in the bottom except for a 1. Okay, what if we have 3 times 3 times 3 over, hopefully you're getting the pattern here, 3 times 3 times 3. This time we have enough on the bottom to cross off every single one on the top, right? So these would literally all divide out, and we'd be left with 1s in all their places. And so we would literally just have, this would just be equal to 1 over 1, right? Which is 1. Now, here is something that's a little bit mind-bending, but 3 to the 0 is also equal to 1. Okay? So save this for later. I'll explain this more later, but for now, we'll just assume that's true so we can figure the pattern out here. Okay, 3 to the 3 divided by 3 to the 4. Well, this time we're going to have 3 times 3 times 3 all over. This time 3 to the 4, so we have 4 of them down below. 3 times 3 times 3 times 3. And now, of course, we have 1 more on the bottom than we have on the top. So as we cross these off, right, we're going to have 1s left over. There's going to be 1 remaining on the bottom that can't be crossed off because there isn't another factor of 3 above here, right? So we're going to actually have 1 over 3, right? And do you recognize this? Could we write this as a power, right? 3 to the something. Well, I want you to think about this for a moment. Here's a trick. If we take this and we flip it upside down, currently, right, this is like 3 to the 1, right, to the minus 1, which is really just 3 over 1 is just 3. So this is equal to 3 to the minus 1. Okay, this next one has 3 to the 3 on top, 3 times 3 times 3. And on the bottom, we have 2 to the 5. So we're going to have 2 times 2 times 2 times 2 times 2. Now, is there any way that we can get rid of the 2's or the 3's here? Well, remember, when we're cross-canceling, we can only cross off common factors, right? So there are no common factors between 3 and 2, right? They're both prime numbers, and they're both very small. So there is no simplification that we can do in this case, and therefore there's no single power that can be done. So again, we had a problem writing this as a single power as soon as the bases became different. Okay, how about here? X to the 4 divided by x squared. Well, this time the bases are the same. So what do you predict is going to happen? We're going to have 4 x's on top and 2 on the bottom. And so we can cross off 1, 2, right? And we're left with 1's in each case. And so on top, we're left with x times x, right? That's equal to x squared over 1, right? Which we can leave out. Okay, and so clearly here, whenever we had the same base and we were dividing powers, right, with the same base, we could literally, we could go 3 to the 3 divided by 3 to the 1 became 3 to the 2, right? So 3 minus 1 equals 2. And here we had 3 minus 2 equals 1. 3 minus 3 is 0. 3 minus 4 is minus 1. Okay? So, and of course 4 minus 2 is 2. So the rule for division of powers is as follows. You can subtract the exponent. So this would be equal to b to the m minus n. So the quotient rule is as follows. To simplify quotients, that's a fraction, remember, right? Or a fraction of powers with the same bases, we divide, or rather, subtract the exponents. Okay, so on the next page, we have a few special cases to look at. The first one is the 0 exponent, and I mentioned this briefly up here, right? When we saw this version with 3 to the 3 divided by 3 to the 3 produced 1, which gave us 3 to the 0. So we'll just look at this one more time, right? If we have 2, all right, if we have 2 times 2 times 2 times 2 all over 2 times 2 times 2 times 2, then essentially, right, we have, you can think of this as well as 16 divided by 16, right? Instead of just crossing them all off, we could multiply it out and we would have this, which is again equal to 1. So anytime you have a power divided by itself, right, or anything divided by itself, you're going to get 1, right? And so that's why, right? Really, we have something divided by itself, and that's why this is equal to 1. But the exponent rule says that if you have a power, right? We just established this. If you have a power, and another one, right? If you have 2 powers, I should say, that have the same base, which is 2, and you divide them, then you can subtract the exponents, right? So this should be equal to 2 to the 4 minus 4, right? Which is 2 to the 0. And so that's how this comes about, this funny exponent of 0. And the general rule here is that any time that you have an exponent of 0 on something, it equals, or it simplifies to 1. Right, so this would be true here if we had 3 times 3 over 3 times 3. Again, this is just 1. And again, with the negative 2's, right? This time we would have negative 2 times negative 2 times negative 2 all over negative 2 times negative 2 times negative 2. And you could expand these, but really you can see quite clearly here that we have something divided by itself, which is always going to be 1. And so in all of these cases, this would be 3 to the 0, right? And this would be negative 2 to the 0. But we would never leave it like this. We would just write this as 1, right? All of these are 1. Simplest way to answer a question ever. All right, what about rational bases? Well, we looked at rational powers of rational numbers, right, at the end of last unit. And so we're just going to be looking at these again really quickly to see if we can speed this process along, right? In last unit, we were writing this out 4 times, right? This 2 to the 3, 2 over 3 to the power of 4, right? So we would be writing, right, in last unit, we'd be writing 2 over 3 times 2 over 3. And this is a lot of work, right? Especially if we have a lot of these to do. So is there a faster way? Well, we know that this is really just going to be 2 times 2 times 2 times 2 on the top, which we actually know is 2 to the 4. And on the bottom, we have 3 times 3 times 3 times 3, right? So that's really just 3 to the 4. So in short, we can write this as 2 to the 4 over 3 to the 4. And the pattern is this. When you raise a rational number to a power, that exponent actually will just literally do its job on both the numerator and the denominator, because it'll end up in both places, right? Here and here. It's the same thing here, right? When we have 1/2. Well, before we would have written 1 over 2 times 1 over 2 times 1 over 2. And we can, of course, write this as just 1 to the power of 3 over 2 to the power of 3, right? So this becomes 1 over 2 to the power of 3. Now, why did I leave it off the 1? Well, we know that this is just going to be 1 times 1 times 1, which is just 1, right? So really, the 3 is still affecting the numerator. It just doesn't show up in the simplified version. Okay, over here, well, for this last one, here, again, we would have had negative 4 over 5 times negative 4 over 5 times negative 4 over 5. So what would this be equal to? Well, again, here, we're gonna end up seeing the 3 affect the 4 and the 5. And what about this negative? Well, remember, when you have a negative base, then you just check, is the exponent odd or even? In this case, it's odd, and so our final answer is going to be negative, right? So this is going to really just be the same as negative 4 over to the power of 3 over 5 to the power of 3. And we can leave the negative out front like that. Or another way to do this is actually to pull the negative up to be on the 4 or the minus 5. So we could write this as well as minus 4, as long as we include it in the cube, over 5 to the 3. Okay, and that's important to do that, right? Because we are recognizing that this minus sign has to get cubed, or or squared, or whatever this exponent happens to be, right? It's going to be affected, so we can't just leave it out, especially if this was an even number, right? If we left this negative outside the 4, outside the brackets, then we would have we'd potentially end up with something that was negative when it should be positive. So the short form, therefore, in this case is going to be, again, minus 4 cubed over 5 cubed. So the general rule, if you have a rational base, a fractional base, and there's exponent, if there's an exponent, it goes to the numerator and denominator. Okay, let's look at part C. The negative exponent. So I've mentioned a bit about this negative exponent before, but in general, okay, in math, we don't leave a final answer with a negative exponent. Instead, okay, what we do is we take the reciprocal and change it to a positive of whatever the exponent is affecting, right? So we take the reciprocal, okay, of in this case, the base or the fraction, and change the exponent to positive. Okay, to a positive version. So, if, let's say we had this, right, 2 to the minus 3, if that was our answer, for example, or let's say we were asked to simplify this, we would not be done. We want to change that 3, that minus 3, to a plus 3. So we have to take the reciprocal. This is 2 over 1. So we write that as 1 over 2. Don't forget brackets, right? And we write that as a positive 3, right? And so we could then go ahead and apply this 3 to the top and the bottom, right? Well, we would end up with 1 cubed on top, which is just 1. On the bottom, we would get 2 to the 3, right, which is 8. And we could be done. How about this one? Well, this time we have 1/4 to the minus 2, right? So this time, we just got to flip it upside down, first of all, 4 over 1, change it to a positive, and then apply the 2 to the top and the bottom. Of course, this is really just 4. So this becomes 4 squared, or 16. The last one, 2/3 to the minus 4, well, again, we'll just take the reciprocal. This becomes 3 over 2 to the positive 4. And then we're going to end up with 3 to the 4, right? This is going to be 3 to the 4 over 2 to the 4, which we could then calculate. 3 to the 4 is 3 times 3 times 3 times 3. That's 81, all right, over 2 to the 4, which is 16. And that would be done. All right, let's look at a couple more examples. So example 1 says, simplify the following expressions using the above rules and verify using a substitution approach. So let's use a substitution approach here, which is what we would normally do with something like this, right? So if we were told, let's say x equals 2, right? Then we could plug 2 in for each x that we see here, right? So we would end up with something like this. We would end up with, well, this would equal, and we'll kind of tuck our brackets in here. So this would be x, we're going to put 2 in for x with brackets, but then there's a 7 above, right? Big bracket. And then inside here, x cubed would become, well, we get 2 again. This time there'd be a 3 up there. All right, lots of brackets. But this would be the way it would be done, right? And then on the bottom, 2 to the 6. Now, to simplify this, of course, we would have to get our calculator out because these are quite large powers. So let's do this. Well, inside this first bracket, we would end up with 2 to the 7, which is, I believe, is 128. And then 2 to the 3, that's not so bad. That's just 8, right? On the bottom, 2 to the 6, 64. And then we have some more calculator work to do. But actually, there's a 128 is actually double 64. In other words, we could divide both of these by 64, and we would get 164 here and 2 here, right? So we would end up with 2 times 8 on the top over 1, which is just 16, right? Okay, so that was quite a lot of work, right? Quite a lot of work. Well, what if we just used exponent laws to make this expression simpler before we do all of this insanity? So, well, what we could do is work with, first of all, on the top we have 2 powers being multiplied whose bases are the same, right? So this is really just the sum of 7 plus 3, right? It's just x to the 7 plus 3, which is x to the 10 over x to the 6. And now, notice how we have really a division, right? So now we can subtract. This is just going to be x, x to the 10 minus 6, which is going to be x to the 4. And so now we know that if x was equal to 2, right? If x was equal to 2, then we would end up again here with 2 to the 4, which is also equal to 16, right? So this is also true. But look how much easier this was, right? What we did is we used the exponent laws to just reduce all of the copies of x, of the powers of x, and combine them into a single power. It doesn't always work quite so cleanly, but often it does. Let's look at number 2. So number 2 says x to the 4 times, and then we have this quotient, right? We have x to the 5 divided by x to the 8. And this is in a bracket, right? So what this means is we need to actually compute this quotient before we do this multiplication. But this is, right, this is a quotient involving powers with the same base, right? And so what we can do is we can leave this x to the 4 nice and happy where it is, and then in here we can subtract. We're going to have x to the 5. It's always, by the way, it's always the first one, the one on the top, minus the one on the bottom. So this would be x to the 5 minus 8, which is minus 3, right? That's a negative number, and you can get negatives when you subtract using the quotient rule. Nothing wrong with that. Now what we're left with is x to the 4 times x to the minus 3. Right? So this, again, here now we have a product, and we can add the exponents. And so this will be x to the 4 plus negative 3, which is x to the 1. And by the way, if you ever have this where you have just an exponent of 1 in your answer, just write that as, just make it invisible. Right? Just write it as x, because anytime you have any number, like 6 or not minus 2 or 12 or any variable like y, that implies a variable of 1. So this, right, and this are actually the same. Okay, example 2. So example 2 says evaluate the following expression for x equals 3 and y equals minus 2 using substitution and then by using the exponent laws. Okay, so let's do this one more time just to drive this point home. Now we already know that using the exponent laws can actually save time, but let's just plug this all in. So what do we have if, well, we take this first, right, this very first step here and write brackets in. So we're going to have x, which is 3. So it's going to be, right, it's going to be 3 to the 4 times y to the 3, and y is minus 2. So we got to put a minus 2 in brackets to the 3. Close off the outer brackets and start this second factor here, and so x cubed is going to be 3 cubed, and y is going to be minus 2 to the 5. And this is all going to be divided by x to the 5, so 3 to the 5 times minus 2 to the 5. And so now look at all the math we have to do, right? We have to calculate all of these powers, right? Because we haven't used any exponent laws here. So let's do it. So we're going to have, in our first bracket, 3 to the 4 is 81, right? And then minus 2 to the 3, well, that's going to be negative 8. And in our second bracket, 3 to the 3 is 27. Minus 2 to the negative 5, that's negative 32. And on the bottom, 3 to the 5 is, let me see, I'm going to have to use my calculator here. It's 3 to the exponent 5. Yeah, 243. Yeah, so at the bottom we have 243. And we have another negative 2 to the 5. So that's going to be negative 32. Okay. So, right, this is a lot of work. And we could continue this way, right? And we would eventually probably get the right answer, right? If we continued with this, as long as we're using our calculator properly and cross-canceling properly, and following the rules. However, there's such a better way. Let's use the exponent laws. So don't do it this way. Instead, let's use the exponent laws to simplify all the powers that have the same basis. So, right, notice how we have x's and we have y's in this expression, right? And the powers of x, you can use the exponent laws on any powers of x that are multiplied or divided, right? Regardless of the fact that there might be other powers in between, like this y is in between x to the 4 and x to the 3, but that's okay, because this is all multiplication. And you can multiply things in any order that you want, right? So we could rearrange this if we want, and it would mean the same thing. So, in other words, let's just take a moment to rearrange things. So this is really the same thing as x to the 4. And I'm going to drop these brackets because really, we can, since it's all multiplication, we can do that. So x to the 4 times x to the 3 times y to the 3 times y to the 5, and that's all over x to the 5 times y to the 5, right? Now in our next step, and by the way, you don't even have to do this step where you rearrange things. You could just literally add these exponents right away, the ones the ones on the x's. So this is really just x to the 7 and times y to the 8, right? So we added the exponents of each of the powers with the same base. And on the bottom we have x to the 5 times y to the 5. Okay. And now do you notice how we have some common factors on the top and the bottom? Or another way of saying this is we have a quotient rule here, right? We have x to the 7 over x to the 5. So this becomes x to the 7 minus 5, which is 2, and times y to the 8 minus 5, which is 3. Okay, now this is so much simpler, right, than what we started with. And once this is as simple as possible, then substitute your values. So we can now substitute for x. So we get 3 squared times minus 2 cubed. Right? And this becomes 9 times minus 8, which is minus 72. And we're done. Let's look now at example 3. So simplify the following expressions. So something happens a little bit differently when you have a power of, a number inside, right? Inside some brackets like this. Well, let's say we don't really know any shortcuts here. Let's just do what we would normally do. We have 2xy as our base, right? Because the 2 is sitting on the whole set of brackets. So we end up with 2xy times 2xy, right? And when you have, right, 2 times x times y times 2 times x times y, literally this is all multiplication. So any things that can be multiplied, that can be simplified, like 2 times 2, you can write that as just 4 in this case. And x times x, well, those both have an exponent of 1, so that becomes x squared. And y, those also have an exponent of 1, so that becomes y squared. So you can kind of see here that the 2, right, became squared, right? It became 4. X became squared, right? It became x squared. And y also became y squared. Okay, and so this distributes to the y, to the x, and the 2. We'll look at that again later in the next lesson, but this is a good preview. Number 2. So number 2 says 1/2 squared times 1/2 to the minus 3. So I included this example because it has a little trick in it. Right? Now what we could do is start distributing the 2 to the top and the bottom of the first fraction. We could invert this one, right? Take the reciprocal, change it to a positive, distribute it to the top and the bottom. But do you notice how what we really have here is multiplication, right, between 2 powers of 1/2, right? So this is really just product rule. And if you notice that, then you can take a great shortcut here. We can just literally add the exponents, right, of each of these two, this base, because there's only one. This is really just 1/2 to the 1, or to the 2 plus minus 3, which is minus 1. Okay, and we wouldn't leave it like this. We have to change that to a positive. So we'll take the reciprocal, 2 over 1 to the 1, and then we just have to clean this up because we don't leave a 1 in the denominator, and we also don't leave a 1 exponent, remember? So we end up with 2 to the 1, or just literally 2, right? Done. Example 3. How about this one? So this one's a little bit trickier, but you can actually use the same strategy that we used for 2 in this question. If you happen to notice that that 2.5, this is really just 5 over 2, right? 5 over 2. I'll just write this. So we have negative 2 over 5 to the 5 divided by, and let's write this as a fraction. Let's respell this as a rational number. That's a quotient of two integers. Well, this is 5 over 2 to the minus 4, right? So all we've done there is just written that as a fraction. 5 divided by 2. Now, one thing that we can do is, well, we could take care of this negative exponent, right? And I'm going to leave this for now as a division. So we'll have negative 2 over 5 to the 5 divided by 2 over 5 to the positive 4. So all we did there is flip this upside down, right? Take the reciprocal and change the exponent to a positive. And we've done that a bunch of times now. Now, do you notice how the bases are starting to look a little more similar, right? They're starting to look a little more similar because we have 2/5. Now, in this case, we have a negative here, right? That presents a little complication, but that's something that we could actually handle on the next step. So watch this, right? If we have -2 to the 5th, we know this is going to be negative in the end, right? And over here, we have +2 to the 5th. +2 over 5 to the 4th, and we know that's going to be positive. And in fact, even if this was negative in here, because we have a positive, we have an even exponent of 4, this, even if it had a negative inside, would also be the same, right? It would be a positive number. In other words, we could just write this as -2 to the 5th, or pardon my language, -2 over 5 to the 5 divided by -2 over 5 to the 4, right? Because this here is going to be the same as that there because of this 4. And so now we have powers with the same base, right? It has to be, and it has to be exactly the same, right? If this was just, if one of these was not negative, like it was here, like these, we cannot use exponent laws on this because the bases aren't exactly the same. Right, so this was just a little tricky question, and now we can use subtraction. We can write this as literally just -2 to the 5 to the power of, and we can subtract the exponents, 5 minus 4, which is just 1, right? And so we can remove this. It's trivial, and we end up with -2 over 5. Okay, so we have one more example. It's a little application. So the M31 galaxy in the constellation of Andromeda is about 2.4 times 10 to the power of 19 kilometers away, which is pretty far. Light travels at about 9.5 times 10 to the power of 12 kilometers per year. Estimate how long it would take light to reach Earth from M31. So, these numbers are given in something called scientific notation, which you may or may not have seen up to this point, but I suspect you have. In any case, they're big numbers, but really we can work with these just like we would with rational numbers and with powers, right? Now, in order to approach this question, we have to look and see what we're asked. Well, we're asked for a time, and we were given, right? We were given a distance up here, right? And a speed, which is how fast light goes. So what I like to do, whenever these three values are involved in a problem, I like to write them in a little triangle. Time, right? Distance, speed, and time. DST. And you put D at the top of the triangle, and you put S and T down below. Now, whenever you're asked to compute one of these, but the other two are given, you just cover up the one you're supposed to find. Right? How long would it take? That's time, right? So if we cover up time with your finger, and look at the other two, we have distance over speed, right? So in other words, time is distance over speed. Okay, so the distance we were given is this. It's 2.4 times 10 to the 19. And on the bottom, we were given the speed is 9.5 times 10 to the 12. Okay, so how could we compute this? Well, first of all, we have some powers here, 10 to the 19 and 10 to the 12, that have the same base, right? And they're part of, this is part of a numerator that's multiplied, right? And again, here, this is multiplied. As long as it's all multiplication, then we can apply exponent laws. So 10 to the 19, this is really going to be 2.4 divided by 9.5, which we can compute separately, times, and then handle this, right? So if we type 2.4 divided by 9.5, you're actually going to get this. You're going to get about 0.2526. So 2526 approximately times 10 to the 19 minus 12, which is 7. All right, and this is quite a large number, 10 to the 7. You punch all of this in your calculator, okay, you're going to get this. It's going to give you 2.526 times 10 to the 6, or spelled out completely, okay, 2,526,000, literally 26,000. Okay, so what does this mean? Well, we were in, first of all, kilometers and kilometers per year, right? So, so the unit here, well, is going to be years, right? This was the time unit that was given. So this literally means 2,526,000 years. This is how long light would take to get to Earth from the M31 galaxy in the constellation of Andromeda. Quite a long time, right? We have a big God to have, to have created such a huge universe. It's amazing. All right, so your practice questions for this section are here. Thanks for sticking with this video. I know it was a little bit longer than you're used to. Give these a try, and we'll see you on the flippity.